So what we're going to work on today is a little investigation of electrolytes and different types of electrolytes. So you know from class discussions and notes that an electrolyte is a substance that dissolves in water and when dissolved produces ions. And we're going to use a conductivity tester to indicate the presence of ions and to a slight extent the amount of ions. What I have here is a light bulb that is part of an incomplete or open circuit. When I plug it in, there's not a way for the electricity to go. There's no path, so the light bulb is off. The first thing I'm going to do is plug this in, and then I'm going to put it in some deionized water. Plug it in, lower it into the deionized water, and you'll notice it does not come on. Okay? And that's because deionized water, as its name suggests, has no ions in it. Now you'll also notice I'm going to be quite careful, so I'm only touching this with the glass stirring rod. I certainly don't want to use anything made of metal, because unlike Mr. Hood and Mr. Conahan, I have no interest in being a good conductor. So I'm going to lift this up, and now I'm going to take an ionic compound. I'm going to take sodium chloride. I'm going to put some solid sodium chloride in. I'm going to lower this in, and once again, I get no light. Now that could be because there's no ions, except there's not a better example of an ionic compound than sodium chloride. But in the solid state, the ions are essentially locked in place in crystals. So the way we can tell is we can dissolve the salt in water, and then the ions become mobile. And even though you may have learned that electricity was essentially moving electrons, it's really moving charges. So when I add the water, the salt dissolves, and now I have a flow of charges. It doesn't matter what the charges are, I now have an electric circuit. The salt did not provide any electricity. That came from the wall. What the salt did was, when it dissolved, the ions in the salt provided a pathway for the charges to make a circuit, or a closed circuit or a complete path. So two things. One, has to dissolve in water, or B, when dissolved, has to produce ions. Now there is another way I could have done this with the sodium chloride. I could have melted it, and then the ions would have been mobile as well, but the temperatures required to melt most ionic compounds are pretty high, so that's not really something I'm going to do for you. So what we're going to do now is test a variety of substances. I've got some strong electrolytes, I've got some weak electrolytes, I've got some non-electrolytes. And what we're looking for is a general amount of brightness. The brighter this is, the more ions. The tester, the conductivity tester, or the light bulb does not care what the identity of the ions are. What it cares about is the number of ions. So this is a pretty qualitative demonstration. So we've already done deionized water, and pure water is a non-electrolyte. Okay? Now what I'm going to do is I'm going to get a strong acid. So for my strong acid, I'm going to pick hydrochloric acid. So I have some hydrochloric acid solution here. I'm going to pour it in. And you'll notice the tester is bright. That's because hydrochloric acid, being a strong acid, is essentially dissociated 100%, so I get a large number of ions. I'm going to pick this up. I'm going to rinse this off with the deionized water, and now we'll do a weak acid. So for my weak acid, I could pick several common acids. I'm going to pick acetic acid. Okay? As a general rule of thumb, all organic acids are weak. So I'm going to pour this in. And I get some brightness out of the bulb, but it's much, much less bright than my strong acid. So this is a weak electrolyte. We would say when put in water, acetic acid produces a small number or few ions. Take this up, rinse it off. Now I'm going to do a strong base. If you remember, the strong bases are hydroxide compounds of groups 1 and 2, or 1A and 2A on the table. So I'm going to use sodium hydroxide. Here's a sodium hydroxide solution. I'm going to pour it in, and it's bright. I've got a lot of ions. And what we generally say for strong acids and bases is that, to a good approximation, they are 100% ionized. Now you might notice this is a little bright, and that's because every time I rinse it, I'm getting a few ions washing in there. So I'm going to replace my deionized water so I'm not bringing ions in. There we go. Now I'm going to do a weak base. Okay? Weak bases are hydroxides from parts of the table other than 1 and 2, so that like aluminum hydroxide, iron hydroxide, or the other one is ammonia. Ammonia is a common weak base. Let's pour some ammonia in. And again, I've got a small number of ions, so ammonia is a weak electrolyte. So for acids and bases, strong acids and strong bases are both strong electrolytes. Weak acids and weak bases are both weak electrolytes. Okay. Next up, I've got some glucose. Good old C6H12O6 from Bio. I'm just going to pour a little bit in, dissolve it in water. Dissolving in water is not enough to make something an electrolyte. Okay? An electrolyte has to produce ions, so even though the glucose dissolves in water, there are no ions. It's a molecular compound, and it's a non-electrolyte. Next up, I have some lead nitrate solution. Okay? This is lead 2 nitrate. Nitrate compounds, as you remember from your solubility rules, are all soluble. So, nice bright bulb. Again, this doesn't tell us anything about the identity of the ions, only the number of them. So as a good rule of thumb, any ionic compound that dissolves in water will be a strong electrolyte. Any ionic compound that does not dissolve in water will be a weak electrolyte. And there really are no medium electrolytes. I've got just 1 or 2 more. This is ethanol, ethyl alcohol. This is an organic compound. So let's see. It certainly dissolves in water. So when I pour this in, I get no ions. So I know this is a non-electrolyte. So there we have our 3 main types. For acids and bases, it's all about whether they're strong or weak. For ionic substances, it's all about whether they're soluble or not. And as you go through the year, knowing your ions and being able to think of things as, do they separate into ions or not, will be really valuable. You did some of this when you did your net ionic equations, or when you will do it when you do your net ionic equations. And as always, the better you know your ions, the easier this will be. For our last piece of the electrolyte demonstration, we're going to light up a pickle. So what I have here are some nice kosher dill pickles, and pickling is an old term that means preserving something by using salt and sometimes spices. So pickles are primarily made by taking cucumbers, putting them in lots of salt and vinegar. So what I have here, I'm just drying this off, is essentially a little container of sodium chloride. And it's aqueous. So this looks like somebody took a lamp cord, split it, and soldered it onto some nails. It's probably not recommended, so don't do this at home. I'm going to put a few paper towels here. Okay. Just as a reminder, no pickles were harmed in this demonstration. And I'm going to plug it in. And let's see what happens. There we go. You might hear something. And what you notice is the pickle lights up and smokes, but it's only lighting up at one end. All right, now this is actually smelling bad. Burnt pickles are not a particularly appealing smell. So we had a couple things you might notice. One, it was yellow, and two, it was only at one end. The yellow color comes from the sodium ions. Sodium ions, when they're energized, produce yellow-orange light. Sometimes that's used in making some light bulbs. So if you see like bright yellow lights, sometimes they have sodium vapor in them. And sodium ions are positive, so this must be the negative end of my circuit, because number one rule of electricity, opposites attract.